What if the greatest mystery of the universe isn't how it began, but why it hasn't ended yet? Because, according to the laws of physics, the cosmos should have collapsed, torn itself apart, or frozen into stillness billions of years ago. And yet it didn't. It kept going, long enough to form stars, planets, and eventually, us. So the real question is this: what invisible forces are holding the universe together, and how long will they keep doing it? 13.8 billion years ago, the universe was born an unimaginably hot and dense beginning. In the first fractions of a second, the temperature exceeded 1 trillion degrees, and space expanded faster than the speed of light. Within a tiny instant, the universe ballooned to a size beyond comprehension. From this chaos, matter emerged. First came quarks and gluons, drifting through a primordial soup. Microseconds later, they fused into protons and neutrons. Matter and antimatter annihilated each other, except for a mysterious imbalance: one extra particle of matter for every billion pairs destroyed. That tiny asymmetry became the foundation of everything we see today. 3 minutes after the Big Bang, the temperature dropped low enough for nuclear fusion. Protons and neutrons combined to form the first atomic nuclei, hydrogen and helium, the building blocks of future stars and galaxies. And their fingerprints remain. 3/4 of all ordinary matter is hydrogen. Almost all the rest is helium, exactly as the Big Bang theory predicts. But as we study the birth of the universe, we inevitably confront its death. No modern physicist believes the cosmos can exist unchanged forever. Its end is not a matter of speculation, only of timing and mechanism. And strange as it sounds, knowing this can be freeing. When you recognize the fragility of the universe itself, everyday worries become small by comparison. The unsettling truth is this: the death of a planet can be survived. The death of a universe cannot. So what will the final moments of reality look like? And will the universe end, or simply transition into something else? The answer depends largely on dark energy, the mysterious force accelerating the expansion of space. If it remains constant, we're headed toward what cosmologists call the Big Freeze. In about 100 billion years, the expansion of the universe will push every galaxy outside our local group beyond the cosmic horizon. The Milky Way and Andromeda will by then have merged into a single supergalaxy. Everything else will fade from view forever. 1 trillion years into the future, the last ordinary stars will burn out. No new stars will form. Only the dim leftovers, red dwarfs, cooling white dwarfs, and brown dwarfs will remain. After 100 trillion years, the universe enters the degenerate era. Planetary orbits unravel. Dead stars collide in rare flashes of light. Most matter becomes trapped inside black holes, temporary islands of structure in an increasingly empty cosmos. Eventually, even black holes will vanish. Through Hawking radiation, they slowly evaporate. A stellar mass black hole survives for around 10 to the power of 67 years. The supermassive black holes at the centers of galaxies may last up to 10 to the power of 100 years. But, in the end, they too disappear. What follows is the age of darkness. No stars, no galaxies, only a thin, cold sea of photons, electrons, and neutrinos scattered across an endlessly expanding space. The temperature approaches absolute zero. Entropy reaches its maximum. Structure, change, and time itself lose their meaning. This is the heat death of the universe. Is there a way out of this fate? Theoretically, yes. A civilization advanced enough could harvest energy from evaporating black holes, slow its internal processes, or encode itself in forms capable of surviving near absolute zero. Freeman Dyson once suggested that life could persist indefinitely by thinking more and more slowly, stretching its moments of consciousness across vast cosmic intervals. But even this is only a postponement. Once the universe reaches true thermal equilibrium, all computation becomes impossible. No gradients remain, no energy differences, no life. Unless physics has a final twist to reveal: quantum fluctuations, vacuum tunneling into new universes, or cyclical cosmologies where each heat death triggers a new Big Bang. Today, cosmologists consider 5 main scenarios for the end of everything. The Big Crunch, where expansion reverses and the universe collapses. Eternal expansion into darkness. The Big Rip, where dark energy tears galaxies, atoms, even space-time apart. Vacuum decay, a quantum bubble that destroys reality instantly. And finally, cyclic models where universes collide and rebirth follows destruction. We understand the beginning, but the ending remains the last great cosmic question. Before we talk about the death of the universe, we need to understand the stories that lead us there. And in this video, we're going to explore 5 different cosmic apocalypses, 5 ways the universe could end. This journey is inspired by the book The End of Everything by theoretical cosmologist Katie Mack, a researcher of dark matter, vacuum decay, and the early universe. I've read a lot on this topic, and nothing comes close to her clarity and imagination. If you can, read the original. It's worth it. Many of us love stories about time travel, not because of paradoxes or time machines, but because the idea itself is beautiful. We move through life, trapped in a chain of now moments, losing possibilities the moment they slip into the past. It makes existence feel strangely wasteful. But cosmology, the science of the universe, offers something astonishing, a way to see the past directly. Not in a practical sense. It won't help you find the umbrella you left on the bus. But for a cosmologist, the past is not a vanished world. It's a real place, observable every day. And it all comes down to a simple fact: the speed of light. Light is fast, but not instantaneous. When you look at the person in front of you, you see them a few nanoseconds in the past. The moon is a second ago. The sun is 8 minutes ago. And the stars? They are years, centuries, millennia in the past. A galaxy 10 billion light years away shows us what it looked like 10 billion years ago, when the universe itself was still in its infancy. Looking into space is looking into history, but there's a twist. We can only see other people's pasts, not our own. The farther an object is, the deeper in the past it lies, and we have no idea what's happening to it right now. So, how do we reconstruct our own past? This is where the cosmological principle enters. On the largest scales, the universe is roughly the same everywhere. Of course, the Earth doesn't look like the surface of the sun. But when entire galaxies become mere pixels, the cosmos becomes startlingly uniform. It resembles a giant cosmic web. Copernicus was right. We're not in a special place. So when we look at a galaxy a billion years in the past, we can say with confidence conditions were probably similar here too. In cosmology, the idea of now starts to blur. A supernova might explode now in our sky, but its light began its journey millions of years ago. Its present is our past. Our present might be another observer's future. Space-time is a strange fabric where different eras coexist. This is confusing and incredibly powerful. It means we can observe cosmic history directly, not just by studying its fossils. We can see the universe at 3 billion years old. When galaxies ignited into brightness, we can see it at 500 million years old, when matter funneled into the first black holes. Soon, we'll be looking at the earliest galaxies, mere hundreds of millions of years after the beginning. With radio telescopes, we might even see the neutral hydrogen that formed before the first stars. But can we see the Big Bang itself? Surprisingly, yes. And the story of how we discovered it is one of the most beautiful in all of science. The signal was coming from space, from every direction. But what could emit perfectly uniform radiation across the afterglow of the Big Bang? They had, quite literally, become the first people in history to see the birth of the universe. In 1978, they received the Nobel Prize. This radiation has become a crucial tool for studying the history of the universe. We can collect data on the glow of the early cosmos and make maps. But how can we be sure that this radiation is indeed from the Big Bang and not from some cluster of stars? The proof is in the light spectrum. Imagine a metal poker left in a fireplace. It glows red thermal radiation in its simplest form. The color of that glow depends only on temperature. A blue object is hotter than a red one. Our own bodies radiate too, but in the infrared, far cooler than fire. Every object in the universe emits radiation across a range of frequencies, but the proportions follow a precise pattern known as a black-body curve. And the cosmic microwave background, the faint afterglow of the Big Bang, matches this curve more perfectly than any measurement in physics. The only explanation is that the entire universe was once incredibly hot. When this result was first presented at a conference, the room erupted in applause. It wasn't just a good measurement, it was the confirmation that we were looking directly at the Big Bang itself. And that faint radiation, mapped across the whole sky, contains clues about the earliest moments of the cosmos. At first glance, the map looks almost featureless, smooth, uniform, quiet. But when you increase the contrast, a mottled pattern emerges. Those tiny spots represent regions of the primordial plasma that were slightly cooler or hotter. Differences in density no larger than 1 part in 100,000. It's like pouring a single can of soda evenly into a swimming pool. Almost uniform, but not quite. Computer simulations take those tiny fluctuations and evolve them forward in time. In seconds, you can watch processes that took billions of years. Slightly denser regions pull in matter, forming the first stars. Those stars gather into the first galaxies. The mottled pattern blossoms into a cosmic web: filaments, clusters, voids strewn with galaxies glowing like beads of dew. And when you compare the simulation to a real three-dimensional map of the universe, the match is astonishing. The early seeds grew into the cosmos we see today. So what came before all of this? About 14 billion years ago, there was no time, no space, no atoms or light, only a singularity, an unimaginably dense point from which the universe was born. That's the traditional picture. But the truth is, we don't really know. Our physics breaks down at such extremes. Quantum mechanics collides with relativity, and the result is mathematical nonsense. We call this moment the Planck time, the first 10 to the power of -43 seconds. An interval so brief that our best theories dissolve in it. We don't know whether tiny black holes formed, whether time itself meant anything, or whether wormholes flickered in and out of existence. After the Planck time, the grand unified era began. 3 of the 4 fundamental forces were merged into one. As the universe expanded and cooled, that symmetry broke. The forces separated. The first particles appeared. Then, a split second later, the universe experienced cosmic inflation, an ultra-rapid expansion of space. In an instant, the cosmos grew exponentially. Tiny quantum fluctuations were stretched to astronomical scales, becoming the seeds of all future structure. When inflation ended abruptly, its energy transformed into a hot plasma of particles. This marked the beginning of the observable universe. During the era of nucleosynthesis, the first atomic nuclei formed. For hundreds of thousands of years afterward, space was filled with a glowing plasma of hydrogen and helium nuclei and free electrons. Photons ricocheted endlessly, trapped in a fog of charged particles like light bouncing through a mirrored maze. After 380,000 years, the universe cooled enough for electrons to bind to nuclei and form neutral atoms. Suddenly, light could travel freely. This light is the cosmic microwave background we observe today, ancient photons that began their journey long before Earth existed. The Dark Ages followed. The gas slowly cooled and thickened into clouds, guided by the gravitational scaffolding of dark matter, an invisible substance that interacts only through gravity, but whose presence shapes everything. Dark matter collapsed first, forming a cosmic lattice that ordinary matter flowed into. After about 100 million years, one of these clouds became dense enough to ignite the very first star. The cosmic dawn began. One by one, stars lit up across the sky like a cosmic string of lights. Their radiation grew intense enough to ionize the gas around them, carving bubbles of transparency around the brightest clusters of galaxies. This was the epoch of reionization. Over the next 13 billion years, galaxies formed and collided. Black holes grew in the centers of massive halos, and countless generations of stars forged the elements of life. The result is the universe we inhabit today, a vast, intricate web of galaxies shining in cosmic darkness. Our blue-white planet orbits a fairly ordinary yellow star in an unremarkable spiral galaxy. But that ordinariness is misleading. Supernova explosions have already seeded billions of worlds with the atoms needed for life. 1 in 10 star systems may host a planet with liquid water. 1 trillion galaxies may hold countless civilizations, each with its own science, art, and origin stories. Somewhere out there, perhaps, another society looks up and detects the same faint microwave glow we do. They learn what we have learned, that the universe had a beginning, that it is evolving, and that it will not last forever. The cosmos is not static. It was born, and like everything that is born, it must eventually come to an end. Look up at the night sky and find the constellation Cassiopeia, the one shaped like a crooked letter W. Just below it, there's a faint blur about the size of the full moon. That blur is the Andromeda Galaxy, and it's rushing toward us at 110 kilometers per second. In roughly 4 billion years, it will collide with the Milky Way, in a cosmic event so vast and so beautiful that, if anyone is still around to see it, it will redefine the word spectacle. Stars will be flung out of their orbits, drawing elegant arcs across space. Colliding clouds of gas will compress, ignite, and create waves of new star formation. In the centers of both galaxies, the supermassive black holes will spiral together and eventually merge in a titanic burst of gravitational waves. And yet, despite all this violence, very few stars will actually collide. The distances between them are immense. The solar system may survive the entire event, though the Earth won't. By that time, the Sun will already have expanded into a red giant and burned our planet to ash. But if some future descendants move their habitats farther out, they could watch this galactic ballet unfold over billions of years. Galaxy collisions like this are common on cosmic timescales. Larger galaxies consume smaller ones. The Milky Way has devoured dozens of dwarf galaxies already. Their shredded remnants still form faint stellar streams, twisting around us. But as spectacular as these mergers are, they're slowly becoming rarer. The universe is expanding. The space between galaxy groups is growing. And that raises a fundamental question. Will this expansion continue forever, or will it eventually reverse? Here's the strange thing. In an expanding universe, every point looks like the center. Technically, there is no center of the cosmos. But from our perspective, every distant galaxy appears to be moving away from us. This isn't about us, it's about the nature of space-time itself, and the ultimate fate of the universe depends on something deceptively simple: the total amount of matter within it. If there's enough matter, the pull of gravity will eventually halt the expansion and turn it around. The universe will begin to collapse in a process known as the Big Crunch. But if there isn't enough matter, then expansion will continue forever. Imagine rewinding a film of the Big Bang, galaxies drifting inward, colliding, merging into ever larger structures, stars sweeping past one another, planets being torn from their orbits, temperatures rising everywhere. But the Big Crunch is not a perfect mirror image of the Big Bang. There's a crucial asymmetry. At the beginning, the universe was nearly uniform, just a hot, smooth gas-filling space. Over billions of years, gravity created stars, galaxies, black holes. Stars have poured energy into the universe, flooding it with radiation. Black holes have unleashed jets of high-energy particles. All of this energy remains in the cosmos. During the collapse, that accumulated radiation doesn't just disappear, it compresses, heats, intensifies. Long before stars physically collide, their surfaces would ignite from the sheer energy density around them. Nuclear reactions would detonate, tearing stars apart and filling the sky with plasma. No planet could survive this. The radiation would reach levels comparable to the central regions of active galaxies, where supermassive black holes fire jets thousands of light years long. And as the universe shrinks, density and temperature rise to unimaginable extremes, far beyond anything we can reproduce on Earth or even describe with certainty. The idea of a cosmic cycle expansion followed by collapse, repeated forever, has a certain elegance. As Katie Mack writes, a cyclic universe has a philosophical appeal. It doesn't begin from nothing or end in annihilation. It simply continues, recycling itself without loss. But the physics is problematic. According to Einstein's theory, if enough matter exists to cause collapse, then the universe begins in a point of infinite density and ends in the same kind of point. What happens between cycles? Our theories fail in those conditions. Worse still, each cycle would accumulate disorder. Entropy would increase. Every new cosmos would be slightly more chaotic than the last. The elegant infinite loop breaks under its own physics. So, let's assume there is no cycle. The question becomes straightforward. Is there enough matter in the universe to make it collapse? Astronomer Fritz Zwicky noticed something strange. Galaxies within clusters were moving far too fast. They should have flown apart like people flung from a wildly spinning carousel. But they stayed together. Something invisible was holding them in place. Zwicky called it dark matter. For decades, few took the idea seriously. Then, Vera Rubin made painstaking measurements of rotating galaxies and proved beyond doubt that dark matter must exist. Without it, spiral galaxies simply don't make sense. Their outer stars rotate far too quickly to be held in place by normal matter alone. But what exactly is dark matter? We don't know. It's probably some exotic particle with mass, one that interacts gravitationally but not with light. Our detectors can't see it, But its effects shaped the universe at every scale. Einstein redefined gravity not as a force, but as the curvature of space. Picture a trampoline, place a heavy object on it, and roll marbles nearby. The marbles curve toward it. Massive objects warp space-time, even light bends. Galaxies act like lenses that distort the light of more distant objects, and that distortion is far too strong to be caused by visible matter alone. Most of the matter in the universe is dark. But even after accounting for all this invisible mass, the key question remained: is it enough to stop the expansion? To find out, scientists needed to measure not just how fast the universe is expanding today, but how that expansion has changed over time. That meant observing extremely distant galaxies and, crucially, measuring their distances accurately. Early analyses suggested the universe would eventually collapse, and the Big Crunch became a popular topic in cosmology papers. But in the late 90s, astronomers developed a powerful new technique, measuring the distances to Type Ia supernovae, exploding stars that act as standard candles. The results shocked the scientific community, earned 3 researchers a Nobel Prize, and upended our understanding of fundamental physics. The universe wasn't slowing down because of gravity. It was speeding up. Not only were we not heading toward a big crunch, the expansion was accelerating. And this discovery led to a disturbing conclusion. If the universe doesn't collapse, it expands forever. But, like immortality, this isn't the blessing it sounds like. A universe that expands eternally is not a paradise. In fact, the most likely outcome is one of the bleakest imaginable. In 1995, astronomers stumbled upon something that simply shouldn't have been possible. According to their best calculations, the universe was between 10 and 12 billion years old. But the oldest stars appeared to be 15 billion years old. In other words, the stars seemed older than the universe itself. And that was absurd. For 3 years, scientists wrestled with this contradiction. They rechecked measurements, refined models, invented new observational techniques. And when they finally found the answer, it was stranger than the mystery they were trying to solve. In the late 90s, 2 competing teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. Everyone took one thing for granted. After the Big Bang, gravity should have been pulling everything inward, gradually reducing the speed at which galaxies recede from each other. The only question was, by how much? To compare the expansion rate in the past with the rate today, they needed objects whose true brightness was known cosmic standard candles. White dwarf explosions, specifically Type Ia supernovae, turned out to be perfect. A white dwarf steals matter from a companion star until it reaches a critical mass and detonates. These explosions always reach the same intrinsic brightness, which makes their distances easy to calculate. Their redshifts indicate their speeds. In 1998, both teams independently arrived at the same astonishing result. The deceleration parameter wasn't just small, it was negative. The universe wasn't slowing down at all, it was accelerating. It was as if you threw a ball into the air and watched it slow down for a moment, and then suddenly shoot upward faster than before. This wasn't just unexpected, it was impossible under all existing cosmological models. At the time, physicists envisioned 3 possible shapes of the universe. A closed universe. Too much matter bends space inward, like lines of longitude on a globe. Such a universe inevitably collapses in a big crunch. A flat universe, perfectly balanced, where parallel lines stay parallel, like on a sheet of paper. And an open universe, too little matter, so space curves outward like a saddle. It expands forever, but its expansion slows. In all 3 cases, gravity should slow the expansion. But the data said otherwise. Something was forcing the universe to accelerate. Something unseen. Something built into the fabric of space itself. Physicists turned to an old idea, Einstein's cosmological constant. Back in 1917, Einstein faced a problem. His equations implied that a static universe should collapse under its own gravity. Everything should pull together. But the night sky clearly wasn't collapsing. So he added a term to his equations, a tiny repulsive force present everywhere in empty space, counteracting gravity. It held the universe in perfect balance. It worked mathematically, but in 1929, Hubble discovered the universe was expanding. The static model was wrong. Embarrassed, Einstein removed the constant and later called it his greatest mistake. But in 1998, the cosmological constant made a triumphant return. Accelerating expansion required precisely such a repulsive force, the energy of the vacuum itself. And then came the real problem. Quantum theory predicts the vacuum energy should be 10 to the power of 120 times larger than the observed value. That's not a typo. Not 10 times, not 100, but 1 followed by 120 zeros, a mismatch so huge it's considered the worst theoretical prediction in physics. No one knows why the cosmological constant is so small. So what is it? One idea is that the vacuum energy varies across space. Our region of the universe might simply be one where the value happens to be small enough for galaxies to form and for life to exist. Elsewhere, it may be different. Another possibility is that this energy isn't constant at all. It could come from an unknown, evolving field. Since we're not sure whether it's truly constant, physicists use a broader term for it: dark energy. A name for everything that accelerates the expansion of space. If this field changes over time, it's sometimes called quintessence, the fifth element imagined by philosophers of antiquity. The advantage of this idea is that quintessence resembles the field believed to have driven inflation in the early universe. Perhaps, like inflation, it will one day switch off. The problem is that a shifting energy field could behave unpredictably. If it ever reversed sign, expansion could halt and the universe could collapse into a big crunch. Thankfully, current observations suggest dark energy behaves like a cosmological constant for now. For the first 5 billion years, dark energy was insignificant. Matter was dense enough for gravity to dominate. But as space expanded and matter thinned out, dark energy grew in relative strength and took control. We see this transition clearly. Distant supernovae show the universe was slowing down in the past. Nearby supernovae show it accelerating today. The tipping point occurred around 5 billion years ago. The irony is sharp. Einstein invented the cosmological constant to prevent the universe from collapsing. And now that same idea may be responsible for its ultimate destruction, just in a very different way. Dark energy makes up about 70% of the universe. It is now the main driver of cosmic evolution. If it remains constant, the universe's fate is heat death, endless expansion, endless cooling, endless emptiness. Dark energy has set the cosmos on a path that cannot be reversed. It has placed the universe on a treadmill that accelerates with every passing moment. Our observable universe spans 45 billion light-years in radius, but visibility has limits. The Hubble radius, about 14 billion light-years, marks the distance beyond which galaxies recede faster than light. Nothing can move faster than light relative to its local space. But these galaxies are not moving through space. Space itself is expanding, and that expansion has no speed limit. So how can we see them at all? Imagine standing on a treadmill that's moving backward. If it slows, you can walk forward and make progress. But if it speeds up too much, no matter how fast you run, you'll be carried away. That's how the universe used to work. Expansion slowed just enough for light from distant galaxies emitted when they were much closer to catch up to us. But dark energy changed the rules. The treadmill is speeding up. Galaxies that cross the Hubble radius are gone from view forever. Dark energy is slowly isolating galaxies from one another. First, the farthest will fade, then closer ones. Eventually, only our local group will remain the merged remnant of the Milky Way and Andromeda. Fresh gas will stop arriving. Stars will exhaust their fuel. Some will explode. Others will cool into dead remnants. Light will fade, and darkness will deepen. And this still isn't the end. What follows is the final, irreversible decay. Stephen Hawking made a discovery that overturned one of the most deeply held assumptions in physics. Black holes, long believed to be eternal objects that swallow everything and give back nothing, were evaporating. Quantum effects cause them to emit a faint glow. The process is slow at first, almost imperceptible. But as a black hole loses mass, it becomes hotter, radiates more intensely, and eventually erupts in a final burst of energy before disappearing entirely. Even the supermassive black holes at the centers of galaxies will suffer this fate. Ordinary matter is not eternal either. All particles decay. Even protons so stable we treat them as immortal will vanish after roughly 10 to the power of 33 years. The last surviving hydrogen atoms, born in the first minutes after the Big Bang, will dissolve. And with that, the universe enters heat death, the triumph of total disorder. The phrase heat death can sound strange when describing the coldest, darkest state imaginable. But here, heat is a technical concept. It refers not to warmth, but to randomness, the chaotic motion of particles and energy. Heat death is not the death of heat. It is the death by heat, energy becoming so evenly spread out that no structure, no motion, no complexity can survive. To understand why, we need to talk about entropy. Entropy is one of the most important and most misunderstood ideas in all of science. It is often described as a measure of disorder. The more ways a system can be arranged without changing its overall appearance, the higher its entropy. A scrambled jigsaw puzzle has higher entropy than the completed picture. A fried egg has higher entropy than a raw egg. Ice, with its orderly crystal lattice, has low entropy. Steam, with molecules flying randomly in all directions, has high entropy. Across the universe, entropy increases relentlessly. This is the second law of thermodynamics. In any isolated system, entropy can only stay the same or rise. Order never increases spontaneously. If you leave a system alone, disorder always wins. Anyone who has tried to keep a home tidy knows this law intuitively. Entropy also explains the arrow of time. We remember the past, but not the future, because the past is more ordered, and the future is inevitably more chaotic. You can temporarily create local order, assemble a puzzle, clean a room, but the total entropy still increases. You sweat, you breathe, you heat the air around you. Every attempt to impose order somewhere creates disorder elsewhere. While physicists pondered entropy in the 70s, a young Stephen Hawking and an even younger Jacob Bekenstein were thinking about black holes. They wondered, could black holes cheat the second law of thermodynamics? Suppose you take a neatly arranged, low-entropy system, a stack of books, a completed puzzle, and throw it into a black hole. From the outside, all that order disappears behind the event horizon. Has entropy gone down? That would violate thermodynamics. Bekenstein proposed a radical solution. Black holes themselves must have entropy, and not just some entropy, enormous entropy. He argued that a black hole's entropy is proportional not to its volume, but to the area of its event horizon. It was a shocking, counterintuitive idea. Hawking pushed back at first. If a black hole has entropy, it must also have a temperature, and anything with a temperature emits radiation, but black holes emit nothing. By definition, nothing should escape their gravity. Then, in 1974, Hawking made his breakthrough. By applying quantum mechanics near the event horizon, he showed that black holes do emit radiation. Virtual particle pairs spontaneously appear everywhere in space. Normally, they annihilate instantly. But near the event horizon, one particle can fall in while the other escapes. To an outside observer, it looks as though the black hole is radiating. This radiation has a temperature tiny for large black holes, but real. Over time, the black hole loses mass, glows hotter, radiates faster, and finally evaporates. This discovery confirmed Bekenstein's intuition. Black holes have entropy, maximal entropy, for any region of space. Hawking and Bekenstein's formula linked entropy to the area of the event horizon using fundamental constants of nature. It was one of the greatest triumphs of 20th century physics. Yet the discovery created a new paradox. What happens to information that falls into a black hole? Hawking radiation appears completely random. If the black hole evaporates, where does the information about the objects it consumed go? Quantum mechanics insists that information cannot be destroyed. This principle unitarity is foundational. If unitarity fails, then quantum theory collapses. This is the black hole information paradox. Either quantum mechanics breaks, or our understanding of gravity and space-time is incomplete. For decades, physicists argued. Hawking maintained that information is lost. But in 2004, he conceded, information must survive. We simply do not know how, but we do know what the universe looks like in the far future. Black holes evaporate. Protons decay, atoms crumble. All matter disappears. What remains is thin radiation dispersed through an ever-expanding void. No galaxies, no stars, no molecules, no structure of any kind. Just smooth, uniform energy in cold black space. This is heat, death, the state of maximum entropy, the final triumph of chaos. And dark energy ensures we reach this state. It accelerates the expansion of space. The more space there is, the more dark energy exists, which drives further expansion. The universe becomes dominated by empty space. Physicists call this future de Sitter space, a condition eerily similar to the early universe during inflation. But inflation ended. If dark energy is truly a cosmological constant, this expansion will never stop. So, is eternal expansion the end of the universe? To answer that, we must return to entropy and to the direction in which time itself flows. As stars burn out, particles decay, and black holes evaporate, more and more matter transforms into free radiation. This radiation spreads through the universe as heat-pure, structureless, disordered energy. The conversion of matter into thermal radiation maximizes entropy. Once matter becomes heat, nothing prevents that energy from dispersing endlessly. And as the universe expands and thins out, the radiation becomes more dilute. It may seem intuitive that lower temperature means lower entropy, but that's not what happens. When the universe enters the stage of exponential expansion, something remarkable occurs. Around any point in space, you can draw a sphere. Beyond the boundary of that sphere lies a region forever cut off from you. No light or particle from that region will ever reach you, not even in infinite time. This boundary is the true cosmic horizon of an accelerating universe. And just like the event horizon of a black hole, this horizon is associated with entropy and therefore with temperature. The difference is subtle but profound. A black hole's heat flows outward, away from the horizon. In a universe dominated by dark energy, the heat flows inward from the horizon into the observable region. The temperature is unimaginably low, about 10 to the power of -40 degrees above absolute zero. But that faint radiation carries the maximum possible entropy of de Sitter space. Once the universe enters this state, entropy reaches its upper limit. And when entropy can no longer increase, the arrow of time vanishes. No more gradients, no more flows of energy, no more change. A universe frozen not in cold, but in perfect disorder. And here come the subtleties, ones that belong not to the category of technically interesting detail, but to the category of this changes everything. The weirdness begins in statistical mechanics, the framework we use to describe temperature, motion, and probability in systems with many particles. Statistical mechanics says entropy increases only on average. It does not forbid temporary decreases due to random fluctuations. Quantum fluctuations can, in principle, create pockets of lower entropy, tiny islands of order, formed spontaneously out of chaos. And in an infinite amount of time, even the most improbable event becomes inevitable. Yes, anything can happen. The universe can briefly conjure a whale, a bowl of petunias, a piano that assembles itself molecule by molecule in an empty box. More importantly, according to the Poincaré recurrence theorem, any state of a sufficiently large system will eventually recur. If the Big Bang is a state the universe once occupied, then in a sufficiently large de Sitter space, it could happen again. A new universe could burst into existence out of a random fluctuation. But runaway weirdness is just beginning. Because if everything can recur, then so can you. Every moment of your life, every thought you've ever had, repeated not once, but an infinite number of times. Cosmologist Andreas Albrecht proposed the idea of de Sitter equilibrium. Our universe itself might have emerged from a rare fluctuation in an eternally expanding background. Sometimes, such a fluctuation produces a full Big Bang. Sometimes it reproduces only a small patch of space, and sometimes hauntingly it recreates something as specific as last Tuesday. It's hard not to think of Nietzsche here. In The Gay Science, he imagines a demon whispering, "You will live this life again and again, innumerable times. Every joy, every pain, every thought, every moment repeated forever." Nietzsche never meant it literally. He intended it as a test of meaning. But physics, bizarrely, offers a scenario where something like this might not be metaphor at all. And this leads to a deeper and stranger possibility, the Boltzmann brain. If an entire universe can emerge from a fluctuation, then a single galaxy is far more likely. A solar system is even more likely. A planet is more likely still. And the most likely of all is a lone, spontaneously assembled human brain, complete with memories, consciousness, and the false impression of having lived a long life in a vast cosmos. A brain floating in a void, hallucinating an entire universe, including this video. Its existence is far more probable than the creation of a whole universe, and that leads to an unsettling conclusion. If we try to explain our world as a random fluctuation, we must accept that it is vastly more likely we are hallucinations, temporary, doomed, self-aware bubbles in a sea of chaos. This paradox is one of the most disturbing problems in modern cosmology, and it reveals a profound truth. If our universe is to be real, if consciousness is to be meaningful, then the cosmos cannot simply be a random fluctuation in de Sitter space. Something deeper must be at work. Cosmologists still argue about this problem. Some believe low entropy states like the Big Bang arise more naturally than small fluctuations. Others think the opposite, that tiny fluctuations are far more likely than an entire universe spontaneously igniting into existence. Carroll calls this idea cognitively unstable, not because it can't be true, but because if it is true, then nothing makes sense. We lose any foundation for reasoning about the universe. Physics becomes meaningless. Yet, even if rare fluctuations occasionally bring pockets of order into the chaos of heat death, the outcome remains bleak. In a universe ruled by a cosmological constant, all structures, every form of life, every machine, every thought faces the same destiny: darkness, isolation, and decay. Before dark energy was discovered, some physicists, including Freeman Dyson, believed that life could stretch out indefinitely. A sufficiently advanced civilization, slowing its computations more and more over time, might survive forever. But the second law of thermodynamics crushes this hope. Even the most perfect machine, operating at an ever-diminishing rate, would eventually decay into heat. All thinking structures vanish after roughly 10 to the power of 1,000 years, a number so large it defies imagination. The exact timescale depends on how long protons survive. And oddly enough, the stable, predictable cosmological constant, the form of dark energy we think we have, is the optimistic scenario. There are worse possibilities. One of them is phantom dark energy, which leads not to slow fading, but to a violent tearing apart of the cosmos, the Big Rip. In standard cosmology, dark energy has a constant density even though the universe expands. That means the total amount of dark energy increases, but its concentration stays the same. This is strange, but at least it's safe. Once structures like galaxies and solar systems form, dark energy won't tear them apart. Matter and dark energy in any region stay in roughly constant proportion. But what if dark energy is something more powerful? Physicists describe dark energy using a parameter called W, the ratio of pressure to density. For a cosmological constant, W equals 1. This produces the negative pressure that accelerates expansion. In the late 90s, physicist Robert Caldwell asked a simple but shocking question. What if W is less than 1? What if it's 1.5 or 2? Until then, scientists had simply assumed W is greater than or equal to 1. Caldwell pointed out that observations did not rule out smaller values. This hypothetical form of dark energy was named phantom energy. It violates some theoretical principles, but nothing in the data contradicts it. And the consequences are catastrophic. If W is even slightly below 1, the expansion accelerates without bound and ultimately tears everything apart. Large structures unravel first. Galaxy clusters disperse. Even the dense core of the Virgo cluster dissolves. Nearby galaxies rush away from the Milky Way faster and faster. Then the Milky Way itself disintegrates. Stars drift away from one another. The sky empties. The galaxy evaporates. The process accelerates. Planetary orbits expand. Months before the end, outer planets fade into darkness. The Earth drifts away from the Sun. The Moon drifts away from the Earth. Everything becomes isolated. But the calm doesn't last. The expansion begins to act on smaller scales. Atmospheric molecules drift apart. Tectonics destabilize. A few hours before the end, the Earth shatters from internal stress. Even escaping in a spacecraft would only delay the inevitable. In the final seconds, electromagnetic forces fail. Molecules disintegrate. Atoms are torn apart. No observer can witness the finale. Even black holes evaporate not by Hawking radiation, but by being ripped apart from within. Finally, space-time itself fractures, and we cannot rule this out. The difference between heat death and a big rip is tiny. If W equals 1, the universe ends in cold darkness. But if W is even 1 part in a billion to billion smaller, then everything ends in a catastrophic tearing. Absolute precision is impossible. According to the most recent data from the Planck satellite, if a big rip does occur, it will not happen for at least 200 billion years. But uncertainty remains, especially due to another mystery, the Hubble tension. The Hubble constant links a galaxy's distance to its recession velocity. The difference seems small, but both measurements are extremely precise, and they do not agree. For years, each side accused the other of systematic errors, but as methods improve, the discrepancy stubbornly remains. One explanation is unsettling. Dark energy may be growing stronger. This would be a signature of phantom energy in a future Big Rip. There are other explanations too. Exotic dark matter, new physics in the early universe, or something else entirely. Whatever the truth, all the cosmic end states, the Big Crunch, the Big Rip, heat death lie in the distant future. But there is one possibility that is far more dangerous, one that does not wait trillions of years, one rooted not in distant cosmic evolution, but in the quantum structure of space itself. It is theoretically well understood, experimentally supported, and it could happen at any moment. In March 2008, retired nuclear safety officer Walter Wagner filed a lawsuit in a U.S. court. He demanded a halt to the Large Hadron Collider, the LHC. In his mind, he was trying to save the world. The case failed, of course. The LHC is run by CERN in Europe, not by the United States. But public anxiety ballooned as the first tests drew near. The LHC was built for the most energetic particle collisions in history. Inside a 27-kilometer ring, protons slammed together at energies recreating the first nanoseconds after the Big Bang. One of its main goals was to discover the Higgs boson, the final missing piece of the Standard Model, the particle associated with the Higgs field that gives mass to fundamental particles. But exploring unknown territory makes people nervous. No one had ever achieved these energies in a lab. No one knew exactly how reality would behave. The internet, filled with apocalyptic speculation, portals to other dimensions, vacuum bubbles, planet-devouring black holes, exotic matter that eats everything. But physicists moved forward. In November 2009, the first collisions took place. The world continued. Years earlier, 4 physicists had analyzed catastrophic scenarios for the LHC's precursor. They dismissed most fears with a simple argument. Cosmic rays perform similar collisions across the universe constantly at far higher energies. If such impacts could destroy the cosmos, it would have happened long ago. The moon has been bombarded by cosmic rays for billions of years. Astronauts walked on it and came home alive. One scenario, however, was harder to dismiss. Vacuum decay, a catastrophic quantum transition. But at the time, there was no evidence that our universe was unstable, so the idea was shelved. Everything changed in 2012 with the discovery of the Higgs boson. To understand why, we must understand the Higgs field, not a particle, but an energy field permeating all of space. The Higgs boson is just an excitation of this field, the way a photon is an excitation of the electromagnetic field. The Higgs field is what gives particles mass. But in the early universe, physics behaved completely differently. Electromagnetism and the weak force were unified. Particles had no mass at all. They moved at the speed of light. Then, a fraction of a microsecond after the Big Bang, electroweak symmetry broke. The Higgs field shifted, the way steam condenses into water. Particles began to interact with this field and gained mass. In that moment, the laws of physics took on their modern form. Symmetry is one of the most powerful ideas in physics. It organizes the universe, the way the periodic table organizes chemical elements. But symmetry-breaking moments, when the conditions change and an elegant theory fractures, are the turning points of cosmic history. The breaking of electroweak symmetry happened 0.1 nanoseconds after the birth of the universe. It reshaped the foundations of reality. We live today in a Higgs vacuum, a state where the Higgs field sits at a particular value that determines the masses of particles, the charge of the electron, and every physical constant necessary for atoms, molecules, and life to exist. If the Higgs field had settled at a different value, we would not be here. The discovery of the Higgs boson in 2012 completed the Standard Model. By measuring the Higgs mass, physicists learned not only the current value of the field, but the entire shape of its potential landscape. And here came the good news and the bad news. The good news, the Higgs mass fits beautifully into the Standard Model. The bad news, that same model says our vacuum may be unstable. Our universe may not be at the true minimum of the Higgs field. It may be perched in a higher energy state, a metastable plateau. The Higgs field could, in principle, slip into a lower energy state at any moment. This is vacuum decay. And if it happens, every law of physics will change instantly. Particle masses will shift or vanish. Atoms will disintegrate. Chemistry, matter, and space-time as we know them will no longer function. And this doesn't happen slowly. It begins somewhere in space, one point, and spreads at the speed of light. A bubble of true vacuum forms. Inside it, the Higgs field has a different value, leading to a different universe with different laws. The bubble wall is a razor of unimaginable energy, annihilating everything it touches. Once formed, the bubble expands unstoppably. We would never see it coming. Anything moving at light speed arrives without warning. One moment we exist, the next moment we don't. Could the LHC have triggered such a catastrophe? No. Cosmic rays have been slamming into Earth's atmosphere with far greater energies for billions of years. If high-energy collisions could destabilize the vacuum, the universe would have ended long before humans existed. But the danger remains. Our universe may simply be metastable, stable for now, but not forever. Like a marble resting in a shallow dimple on a hillside. Quantum fluctuations could push the Higgs field over the edge at any moment. Tomorrow, or never. We cannot calculate the probability with precision. And here lies the irony. The discovery of the Higgs, the crowning achievement of modern physics, also revealed the fragility of our existence. The very theory that explains why matter exists simultaneously predicts that its stability may be temporary. We may live in the most precarious of all possible universes, stable long enough for life to emerge, but not stable enough to last indefinitely. The idea isn't new. Physicists wrote about vacuum collapse mostly as abstract mathematics with no experimental support. Now, the support exists. To visualize the danger, imagine the Higgs field as a small pebble resting on the side of a valley. The landscape of hills and dips is the field's potential. The pebble seeks the lowest point. The problem is that the valley floor may lie much deeper than where the pebble rests now. As Katie Mack writes, the Higgs vacuum can only be called metastable. The field sits in a minimum that is more like a pocket on a hillside than the bottom of a valley. It can stay there long enough for galaxies and stars and life to form, but a strong enough disturbance could push it over the edge. And she continues, unfortunately, the best data we have, fully consistent with the standard model, suggest that the Higgs field is in precisely such a state, a false vacuum, rather than the true one. What's wrong with a false vacuum? Everything. A false vacuum is temporary by definition, and when it decays, the transition is instantaneous, clean, silent, and absolutely final. It destroys not just matter, but the possibility of matter. Not just life, but the possibility of life. Something must trigger the transition. A colossal cosmic explosion, the evaporation of a black hole, or simply quantum tunneling. The Higgs field might randomly pass through the barrier separating the false vacuum from the true one, the way a particle can sometimes appear on the other side of a wall. If it happens anywhere, the end begins. A pinprick bubble of true vacuum forms. Its wall expands at nearly the speed of light. Everything it touches undergoes total dissociation. Atoms fall apart. Forces break. Matter loses the meaning of matter. You don't see it coming. You don't feel anything. There is no after. As Mack writes, the bubble will not stop with you. Entire planets, stars, and galaxies will be destroyed. Only regions forever beyond the bubble's horizon due to cosmic acceleration will escape. And she adds, with characteristic dark humor, it's entirely possible that vacuum decay is already happening somewhere, perhaps beyond our cosmic horizon, consuming galaxies we'll never see. Or perhaps, cosmically speaking, it began right next door and is already racing toward us. But don't lose sleep over this. You can't stop it. You can't predict it. And you wouldn't feel it, even if it arrived right now. The good news is that the energy required to trigger vacuum decay is unimaginably large, greater than anything we've ever observed, even in the most violent cosmic explosions. The barrier between false and true vacuum is high. Except, and here, quantum mechanics pulls one last trick. The universe doesn't need the energy to climb over the barrier. It can simply tunnel through it. As Katie Mack puts it, our cosmos is based on quantum mechanics. And quantum mechanics tells us that if you exist on a subatomic scale, sometimes the path you take can go straight through the wall instead of over it, especially if you're a Higgs field. Quantum tunneling may sound like wild speculation, but it's not science fiction. It happens constantly in the real world. Engineers designing your phone take into account that an electron can simply appear on the other side of a barrier, inside a microchip. Scanning, tunneling microscopes use this effect to image individual atoms. If electrons can tunnel, so can fields. The Higgs field can, in principle, tunnel straight into a lower energy state, a true vacuum. The wall that separates us from a cosmic catastrophe is not a brick wall. It's more like a high, thin fence. The good news is that even quantum tunneling plays by rules. We can calculate the probability. The bad news is that probability is all we get. No schedule, no countdown. The Higgs field could, in theory, tunnel and create a death bubble near you in the next 30 seconds. But that's so unlikely it's not worth worrying about. The best estimates suggest our vacuum will survive for roughly 10 to the power of 100 years. By that time, either heat death or the Big Rip will have gotten to us first. Compared to those, instant annihilation might even start to sound merciful. Recently, physicists added another twist. In 2014, researchers showed that black holes can catalyze vacuum decay. Tiny black holes no bigger than particles are especially dangerous. They can act like seeds, nucleation sites for bubbles of true vacuum, the way dust grains help water condense into droplets in humid air. Fortunately, creating such black holes appears extremely unlikely. As far as we know, black holes form when massive stars collapse. Once formed, they evaporate only through Hawking radiation, a process that takes around 10 to the power of 64 years for a solar mass black hole. It's possible that microscopic black holes formed in the extreme densities of the early universe, but we have no evidence for them. And if they were efficient at triggering vacuum decay, we wouldn't be here. Some physicists actually hope to make tiny black holes in colliders. That would require extra dimensions of space, which would strengthen gravity at very small scales. Producing a black hole at the LHC would be a spectacular confirmation of higher dimensions, a dream scenario for particle physics. It would also raise the uncomfortable question of whether such an object could kick off vacuum decay. In 1980, Sidney Coleman and Frank DeLucia analyzed exactly this kind of scenario. A bubble of true vacuum, they argued, wouldn't just contain new particle types, it would correspond to a region of spacetime that is gravitationally unstable. Its contents would collapse in microseconds. They summed it up bluntly. Vacuum decay would be the ultimate ecological disaster. In the new vacuum, chemistry as we know it wouldn't exist. Nothing resembling life could arise to enjoy whatever universe followed. Vacuum decay is a young idea, born from extreme physics and delicate calculations. Our picture of it may change. Some analyses suggest that a metastable vacuum might be incompatible with cosmic inflation. The violent fluctuations in the early universe should have kicked the field into its true minimum. And yet, here we are. Serious worry about vacuum decay relies on trusting the standard model at energies we've never tested. But we already know the standard model is incomplete. Dark matter, dark energy, and the clash between quantum theory and gravity all hint that a deeper framework is waiting. Whatever replaces our current theory might free us from the threat of a quantum death bubble. Or it might reveal new, even stranger ways the universe could end. On the 14th of September 2015, at 9, you were stretched very slightly taller, not enough to notice less than a millionth the width of a proton. A gravitational wave passed through you, gently warping space. It had been traveling for 1.3 billion years, ever since two black holes collided and merged. Detectors at the LIGO Observatory picked it up. This first detection of gravitational waves was a triumph of experimental physics and a stunning confirmation of Einstein's theory. More importantly, it opened a new window on the universe. For the first time, we weren't just seeing light from distant events. We were feeling the vibrations of space-time itself. Gravitational waves don't just tell us about black holes and neutron stars. They give us a new probe of gravity under the most extreme conditions. And gravity is the odd one out among the forces of nature. Mathematically, it looks different. In everyday life, it feels incredibly weak. Every time you lift a coffee cup, you overcome the pull of an entire planet. For gravity to compete with the nuclear forces, the mass of the sun would have to be squeezed down to the size of a city. Physicists dream of a theory of everything that unifies gravity with the other forces. We've already unified electromagnetism with the weak force. There are ideas for unifying all three non-gravitational forces in a grand unified theory. But every time we try to bring gravity into the picture, something breaks. General relativity and quantum mechanics give different answers about what happens at the edge of a black hole. They disagree about what happens at the beginning of time. There are several ways out. One is that we abandon the dream of unification. Maybe there is no single elegant theory behind everything. Another is that we've misunderstood gravity. Maybe general relativity is only an approximation, and it needs to be extended or replaced. Quantum gravity theories attempt exactly this. They treat gravity as a quantum field with particles gravitons, whose collective behavior looks like curved spacetime. But after decades of work, no candidate theory has been confirmed. The effects show up at energies far beyond what our accelerators can reach. So we look upward to cosmology. The early universe is a far more powerful particle collider than anything we can build. Dark matter and dark energy are already screaming that something is missing from our picture. The matter-antimatter imbalance is another unsolved puzzle. Yet, general relativity keeps passing every test we throw at it. Perhaps gravity is fine, and something else is strange about the universe that makes gravity appear weak. One radical idea is that gravity leaks into extra dimensions. We usually think of space as three-dimensional, plus time. But there could be additional spatial dimensions curled up or extending beyond our perception. Our universe might be a three-dimensional brain embedded in a higher dimensional space. Gravity, unlike other forces, could spread out into these extra dimensions, weakening its apparent strength in our three-dimensional world, like ink soaking through a stack of paper. If that's true, our brain might not be alone. Other universes, other brains, could float nearby in the higher dimensional space, tugging on ours through gravity. Collisions or interactions between brains could create new universes, and they might one day end ours. This idea inspired one of the most intriguing alternatives to standard inflation, the ekpyrotic universe. The name comes from an ancient Greek word for a cosmic conflagration that destroys and renews the world. In the ekpyrotic model, our universe is a three-dimensional brain drifting in higher dimensional space alongside others. The Big Bang wasn't the beginning of everything. It was the moment two brains collided. After the collision, they recoiled and drifted apart. Over vast timescales, gravity could pull them back together, setting up another collision, another Big Bang. If this model is right, our universe has no absolute beginning or end, just an endless sequence of bangs and rebounds. In 2014, a team of scientists announced they had detected signs of primordial gravitational waves in the polarization of the cosmic microwave background, potential evidence for inflation. The excitement was enormous. If confirmed, it would have strongly disfavored ekpyrotic models. But later analysis showed the signal could be completely explained by dust in our own galaxy. The primordial waves weren't there. That doesn't mean ekpyrotic models are correct, but it keeps them alive. Other observational clues may come from gravitational waves. Some theories predict subtle signatures, tiny distortions in the signals from black hole mergers that would hint at extra dimensions. So far, the data has put tight constraints on many of these ideas. Regardless of extra dimensions, the broader idea of a cyclic universe remains attractive. One reason is entropy. In standard cosmology, entropy always increases, leading inevitably to heat death. But the universe seems to have started in an extraordinarily low entropy state. Why? Cyclic models attempt to answer this by pushing the entropy problem back into a previous cycle. In some versions of the ekpyrotic model, all the entropy we see today corresponds to a tiny patch of the prior universe. There's no singularity. The universe contracts only modestly, perhaps by a factor of 2 before bouncing. Space never shrinks to a point. If this picture is right, then in the far future, we would see distant galaxies slow, stop, and begin to move closer. It would look like the beginning of a big crunch. Background radiation would heat up. But long before we understood what was happening, the energy of a scalar field would violently convert into radiation, triggering a new Big Bang. The cycle would continue. Gravitational waves from earlier cycles could, in principle, survive, whispering information from a previous cosmos. Other bounce models go even further. Roger Penrose's conformal cyclic cosmology proposes that the distant future of one universe after heat death is his view. The singular boundary between eons has special properties that allow entropy to reset. Neil Turok has suggested an even more radical picture. The Big Bang as a transition between our universe and a time-reversed anti-universe. Two cones touching at their tips, one opening toward the future, the other toward the past. Such models can address both entropy and dark matter and make testable predictions. So where does that leave us? Was the Big Bang a unique event or just one chapter in an endless cosmic cycle? Is our universe doomed to fade into darkness, tear itself apart, or be erased by a quantum bubble? Will new data from gravitational waves, particle physics, or cosmology finally reveal the true shape of spacetime and the true ending of our story? We don't know, and we may not find out within a single human lifetime. But that's not a failure, it's a feature. Right now, the sun still shines, the Earth still orbits, the universe is still full of structure, complexity, and thought. We have time to build telescopes, colliders, detectors, to test ideas about extra dimensions, false vacua, and cosmic cycles, to tell stories about the end of everything, even as we continue to live. Whatever the ultimate fate of the universe, crunch, rip, freeze, bounce, or something stranger, we are here, now, able to ask the question, what comes next?